You have chapter 9 for me? On Friday, we did an example using the summary data for our means and standard deviations. We were told that the variances were equal. And because of that, we were able to use a pooled variance. But if we don't know that, then I can do the unequal variance version. Remember, the formula is slightly different for the unequal variance, and we have to make the adjustment for the degrees of freedom. That's this formula here at the top of page 369, or if you'd rather, the summary version down here, but the summary version doesn't contain the degrees of freedom issue. So if I wanted to do that same problem with this formula, I wouldn't be able to pull the variances. I have to use S1 squared and S2 squared here instead of a pooled variance, and I have to change my degrees of freedom. In the Excel spreadsheet on our Canvas page, I did that, and our degrees of freedom went from 26 to 24, 27 to 24, went down by a few. Again, I need to do this calculation and then round it down. But that actually gives me a slightly different result, and thus can change my decision. So the question becomes, which is a better choice? Should we make the assumption that our variances are equal and run with our decision that way, or should we make the change to our degrees of freedom, loosen our restrictions slightly, and do it that way? I am of the opinion that if you have different sample sizes, you're better off doing the unequal variance test. But it's a more complicated calculation for degrees of freedom. The problem is that it sometimes allows us to increase our type 1 errors. We reject a true null hypothesis. In a lot of cases, this is a matter of what's statistically significant versus practically important. Does this make a real difference? Really, we want to think about what our underlying population looks like. Is it skewed? Does it have outliers? Do we have relatively centralized, normally distributed data, or do we simply not know? In which case, increasing our samples may be beneficial. I want to do another one. So here is problem 9 on page 375. For a marketing class term project, Bob is investigating whether college seniors eat less frequently in fast food chains than the freshmen. He asks 11 freshmen and 11 seniors to keep track of how many times they ate at a fast food restaurant during October. So these numbers represent the number of times the student went out to eat at a fast food restaurant during October. If I assume variance among students is the same, is his hypothesis true? Do college seniors eat less often at fast food restaurants than college freshmen? Based on this information, I got to go through the whole thing here. What's my null hypothesis for this problem? My null hypothesis. Which of the three am I working for? Is this a two-tail test or a one-tail test? Because so I'm going to use one of these two. It depends on which population I call population 1 and which population I call population 2. So if I know which population is 1 and which population is 2, that'll tell me which tail I'm going to use. I'm going to read the question the way they put it out. Do seniors eat less frequently than freshmen? Seniors eat at fast food less often than freshmen. And then I look at the data again. And the way the data is organized in this particular spreadsheet, seniors are in column 1, freshmen are in column 2. Let me continue with that. So I'm going to label the seniors as group 1 and the freshmen as group 2. Now, what do we want to determine? So I want to know if the average for the first group is less than the average for the second group. That should be my alternate hypothesis. Or another way to write that is that the difference between these two is less than or equal to 0. If that's the alternate hypothesis, what's the null hypothesis? Greater than or equal to. Okay, wait a minute. That means the exception is in my left tail. This is a less than. We are doing a left tail test. Now, I have all the individual pieces of data here. I'm going to do this entire process in Excel. So, what I'm going to do is I'm going to go to the Data tab, and I'm going to go to Data Analysis. And under Data Analysis, I'm going to do a t-test because I have small groups, right? I only have 11 in each group. And I said, assuming equal variance, it was in the problem that way. I'm going to click on that middle one, says 2 samples, assuming equal variance. And it asks me, where's group 1? Here's group 1. Where's group 2? Here's group 2. And I did put labels in my ranges. See how the freshman is included in the box? So I'm going to click on labels. And my hypothesized mean difference is 0. I don't think they're different. I think they're either the same. And what I'm comparing to 0. And it says at the 5% level of significance. So 1 minus alpha is 0.5. That means alpha itself is 95. There's my 95% there, alpha 0.05. Right there, that's what I needed. I want to put all of this in a new worksheet ply, so I'm just going to stick this in a new worksheet. It'll do all the work for me. Click, oh, I hit enter there. There we go. Here's my new sheet. Great. So what? It did all the hard stuff. It did the work. What does it mean? There are two different ways for you to answer the question that we were asked based on this information. Do I accept or reject my null hypothesis? Our alpha was 0.05. That's too small. We're in the rejection area. Reject the null hypothesis. What's the other way I could have done it? Now I actually see the words a little better. But that wouldn't tell me enough. That just telling me what the difference in the means are is not sufficient. I need to know how it compares to the standard deviation. That's why that's divided by the standard error, right? S1 squared over N1 plus S2 squared over N2. So just looking at the difference in the means isn't sufficient here. I mean, there is clearly a difference in the means. 10.6 versus 14.1. Yeah. Freshmen seem to eat out more. But is it statistically significant? I got one answer that says yes, but what's my other method? Check the p-value or calculated T versus critical T. Do you see something up there that says critical T? I see two different critical T's, right? One that says one tail and one that says two tail. So I need to know which version I'm doing. I'm doing a one tail test, so I'm going to use that T that says critical one tail. Now, mind you, that's the positive number. But since we're doing a left tail, we want to deal with absolute values or to think of the negative version of that number. Where is my calculated T value? They didn't actually label it T calc. They labeled it T stat. That's this one right here. If that number in absolute value is bigger than our critical value, then we're in the rejection region. Do our two results agree? Yeah. Negative 1.8 is smaller than negative 1.72, or positive 1.8 is bigger than 1.72. So we're in the rejection area, and the p-value is smaller than 0.05. We're in the rejection area. This makes sense both ways. If I get contradictory results, we have a problem. So according to this, yes, this is a statistically significant difference. Our seniors eat out at fast food restaurants less than our freshmen do in this group. But it's close, isn't it? 0.04 versus 0.05. Pretty close. On the other hand, 10.6 versus 14.1. Is it practically significant? How much is a meal at a fast food joint? Okay, it's $15 and you eat out 3.5 more times. You're talking $55, right? It's not cheap. The freshmen spend $55 more in October on average than the seniors do. Now, our straight data just shows the averages. The summary data gives me an information idea here. Now I could say, hey, if you were to do what the seniors are doing, you'd save $50 a month. I tested this with equal variances. But data analysis, the t-test for unequal variances is right there. So if I do that one, again, same data. Click on labels, hypothesized mean difference is 0. I got the same thing. My probability for my one-tail test is still 0.04, which is smaller than 0.05. This says reject the null hypothesis. We did do different math, though. How do I know? DF on this test was 20. 11 plus 11 minus 2. The DF on this test was only 19. So our increase in the degrees of freedom loosened our setup a little bit more, but because we made that assumption and used the actual variances, we got a different answer. And again, seeing the variances calculated, 24 versus 15.7, those numbers are the same here. Those came from our actual data. That's the S value, not the population data. If I didn't know that seniors' dining habits and freshmen dining habits were substantially different in advance, I wouldn't be able to make that assumption automatically. I still get the same results. Again, it's still close. 0.05 versus 0.042. It's only just barely outside of our region of confidence. Questions? I had done these both before. Okay. According to this, we reject our null hypothesis, and we can conclude then that the seniors do eat out at fast food restaurants less than the freshmen. Again, given the data, you could do this entire test in here. Under stat, tests, 2-sample t-test. Whether we want it two-tail, left tail, or right tail, whether we're doing pooled variances or not, whether we're using the data in our lists or whether we're doing the summary statistics. And then we just tell it to calculate. If I put all those 11 numbers in list 1 for the seniors and 11 numbers in list 2 for the freshmen, I can do that entire thing here. I like my calculator. Questions? Could also have gotten the calculated, the critical t-value from my table against the calculated t-value if I had to do the calculation by hand. I said something particularly interesting. Nobody blinked. If we looked at this p-value and said it was 0.042 and compared it to 0.05, we're in our rejection region. We're outside a confidence interval. I want to define a confidence interval. And then I can think of this entire test a different way. I have an expected difference between my two means. Now, in this last problem, the expected difference was 0. So I should look at the confidence interval and say, hey, does this confidence interval contain 0? Yes or no? If it contains 0, then it contains my expected difference, then there's no difference between the two things. But if my confidence interval doesn't contain 0, it doesn't contain my expectations, then we should reject. In other words, a t-test or a z-test is really checking, are we in the confidence interval or out of the confidence interval? Which means my confidence interval calculation is going to look just like my t-tests rearranged. If I'm using a pooled variance, I'm assuming that the variances are equal, sigma 1 equals sigma 2. Then I'm going to use the T alpha 2, T alpha over 2. So for a two-tailed test, remember, a confidence interval is always two-sided. Always. And since I'm using the pooled variance, I'm going to use this number for my degrees of freedom. I take my calculated difference, and then I add or subtract T alpha over 2 times what? When we did a confidence interval and the stuff that you gave me in chapter 8 that you already got back, what went next to that T value or Z value to figure out a confidence interval? the standard error. And the standard error for here is the ugly sucker. And then we adjust for the pooled variance setup with this extra square root on the end. This is another way to get at the pooled variance without doing that calculation separately. Now, I'm the first person to tell you, again, it's a calculation that is ugly to do by hand. And if all I have are summary statistics, I'm either going to have to do it by hand, or I'm going to have to shove in those summary statistics into a calculation device, whether or not they actually happen to generate a confidence interval. Again, confidence intervals are down here. 2 sample T interval, 2 sample Z interval. They're available. And again, I can do it with my summary statistics. So, a test. Question number 11, page 377. In trials of an internet-based method of learning statistics, hey, we're going to do our classes online. Post-tests were given to 2 groups: traditional instruction, face-to-face, 22 students, and internet-based students, 17 of them. On the post-test, the traditional group had a mean of 8.64 and a standard deviation of 1.88. Since they listed this group first, I'm going to call this group 1, and I'm going to label all of these pieces of data as N1, X bar 1, and S1. The internet students, which had a group of 17, had an average of 8.82 and a standard deviation of 1.7. Construct a 90% confidence interval with a true difference, assuming equal variances. Okay. Assuming equal variances would mean if I were to do this by hand, I'd use this formula. I have never done this on my calculator before, people. We're going to do it right now here for the very first time. 2 sample T interval. I'm going to input the summary statistics. Hey, it asked me for the standard deviation and mean for the first group, 8.64. Standard deviation was 1.88. And there were 22 people in that group. Second group, 8.82, a standard deviation of 1.7, and there were 17 in that group. Now it asked for a 90% confidence interval. I'm going to put in 0.90 there. And it said equal variances. That means I pool stuff. And now I can calculate my confidence interval. Think. Hey, a lot of stuff. Okay, wait a minute. First question. So what? What does this confidence interval tell me about the difference between people who took this post-test online versus people, sorry, people who took the class online versus people who took the class face to face. Look at this confidence interval. The true mean difference between these two is between negative 1.163 and 0.803. What's in the middle of there? Somewhere. And if zero is in the middle, then the true difference between these two, I'm at least 90% confident is in here, it might as well be zero. Are these results statistically different from one another? No. In this group of 22 and this group of 17, there's really no difference as to how they did on this test based on this set of data. Now, I did this by hand because I'm that kind of geek. I did all the same work and I got the exact same freaking numbers. Oh, thank God I don't have to do it by hand. Questions? Okay, wait a second. There was a big if at the start of this. If we are using pooled variances. And I can only do that when I assume my variances are equal. But what do I do if I don't know that the variances are equal? What changes when we don't pool the variances? And if my degrees of freedom change, then that standard error is going to change. So if I wanted to do this same thing without a pooled variance, I'm going to get a different t-value because I'm going to have a different degrees of freedom. And if I have a different degrees of freedom, I'm going to end up with a slightly different interval. Now, again, I feel pretty happy because in this same setup, all I have to do to change this is to go through here, go all the way down, and change the pooled from yes to no. That's the only difference I need to do. And when I do this, I get a different interval. It's not a lot different. My degrees of freedom is different. See, 36.02 as opposed to the in the previous version, it's population 1 plus population 2 minus 2. 22, 17 minus 2 is 37. Just barely different. It's 36 versus 37. But that changes my t-value and it makes my interval different. This interval is slightly narrower than the first one. The first one was negative 1.16 and 0.803. This is negative 1.15 and 0.791. It's just barely different. It's just a little small. It's only about 1% small. But it does give us a change in the way to look at this. Again, zero's in that interval. If zero's in that interval, I don't need to say these are different. My data doesn't support them being different. My data says these groups are about the same. Now, I could do something else. Oh, I could also ask you to do what you did in chapter 8 and do a confidence interval for each individual mean. Okay, wait a minute. I need to write down the numbers again. Traditional N1 was 22, X1 bar was 8.64, S1 was 1.88. In the internet group, N2 was 17, X2 bar was 8.82, and S2 was 1.70. I want to ignore for the moment that we're doing separate calculations. I'd like a confidence interval for each mean, a 90% confidence interval. $90. Okay, wait a minute. I need a formula for the confidence interval for each mean. All right, wait a minute. For a mean, that's X bar plus or minus T alpha over 2 S over square root n, our standard error. I'm going to do this one by hand because I have the t-table sitting right here in front of me. First group, n is 22. So for the traditional, that means the degrees of freedom is 21. And so I need T 0.05. Alpha is 0.1. Half of that is 0.05. DF is 21. 90% confidence. 21, 1.721. Okay, so it's 8.64 plus or minus 1.721. Standard deviation is 1.88 over square root of 22. Somebody give me this number. Whatever's supposed to go here. Good enough? So when I add or subtract, I get 7.95 and 9.33. So that's my confidence interval for the first group. What's my confidence interval for the second group? Again. Only this time, population size is different. Population size is different, the t-value is different. Fewer people, so I use different degrees of freedom, and this time I get a different t-value. Repeat the process. Only I'm using the numbers up here for the internet group.
Lower and 9.539.
I'm rounding. But yeah, there we go. Hey, wait a minute. In our previous discussion, we said the interval contained 0. So these two samples are basically equivalent. How do I know whether or not these give me that same information? Look at the overlap of my numbers here. The first interval goes from 7.95 to 9.33. So there's interval number one. Interval number two goes from 8.1 to 9.54. There's a whole lot of overlap in there, isn't there? If there's a whole lot of overlap, then I can say with some level of confidence, the means for these are probably the same. If they overlap a lot, that difference should be zero. Questions? This question was about students taking a stats class in one of two different formats. They either took it in person or they took it online. But sometimes what we want to do is test the same person before and after something. Or I want to test the same product being done before something happened and after something happened. For example, a new treatment for tires claims to make them last longer. So I run the tire. For a while, I measure the wear, I treat it, I run it again. Same tire, two different ways. How do I account for the fact that here, the samples had nothing to do with each other? But in this discussion that I've just had about tires, it's the same sample two different times. I'm going to have to look at what changes when I relate my samples to one another. And that is what we will discuss on Wednesday. I will see you all then.